Hello everybody. The following question was suggested by Rob. So thank you, Rob. This is your semicircle shaped wall. You want to build a rectangular window. 2 points of this rectangle are supposed to be on the arc and the other 2 on the diameter. Your goal is to make this area as large as possible.
First, let's start with our construction. We have a semicircle and now we want to build the area of this rectangle. We will form an area by adding perpendicular lines from this point, P. We only have to look at this half of the rectangle since it's clearly symmetrical to the other half. Maximizing this area maximizes the area of the whole rectangle. We call this side A. The radius is given to us. Using the Pythagorean theorem, it's not difficult to see that this side is of length r squared minus a squared. That means that the area of the rectangle is a times r squared minus a squared. We can see this as a function with the variable a. Now we just have to find the derivative of this function and set it to 0. Let's find the derivative of this function. Starting off, we are going to use the product rule. The result that comes is this. We now have to use the chain rule, which brings us to this. That is the derivative of the function. We just have to set it to 0 now. Multiplying by square root of r squared minus a squared, we get this, which eventually simplifies to a square is equal to r squared divided by 2. Looking back at our configuration, the formula we got for half the area is this. We just have to put in the value for a in there. Thankfully, this simplifies to r squared divided by 2. As said before, this is only half of the area. To get the whole area, we multiply it by 2.
Hold up, we are not finished yet. Just because we set the derivative to 0 doesn't mean we have found the maximum. It just means that the slope of the tangent at that point is 0. We could also be at the minimum, so we have to clear that up real quick. Graphing our function gives us this. If we recall, setting the derivative to 0 gave us this result, but now we have to take the square root of it. This gives us a positive and a negative result. And in our graph, it is also not that hard to see that there is a maximum and a minimum. The negative result gives us a smaller value than the positive result. So the negative result is the minimum, and the positive result must be the maximum. Great, but now let's try doing it a different way. The construction basically stays the same. We'll just use angles this time. Let's call this angle alpha, and we know that the radius is r. Simple trigonometry says that these sides are r times sine alpha and r times cosine alpha. Now this is the area we want to maximize. Combining the r's, we get r squared times sine alpha times cosine alpha. To continue from here, we're going to use a trigonometric identity. It says that sine alpha times cosine alpha is equal to sine of 2 alpha divided by 2. Using this, we get this simple function. We now have to find the maximum of the sine function, which is 1. So that's it. We didn't even have to differentiate this. Great, now we know that the maximum area is r squared. Let me show you something interesting. Just follow along. We have a circle and 4 points. If we connect the points like this, we get a cyclic quadrilateral. Let's name the sides from A to D. One property of such a quadrilateral is that the addition of the opposite angles are 180 degrees. So if this is alpha, this angle is 180 degrees minus alpha. We want to find the maximum area of this quadrilateral. Let's split it into two triangles. We now know that the area of this triangle is this. But sine of 180 degrees minus alpha is just the sine of alpha. The other area is similarly this. Now we know that the total area is the addition of the areas of the triangle. Now let's take a closer look at the length of the side AC. We can use the cosine rule to get these two equations from both the triangles. They're both equal to each other, and through them we get the value of cos alpha. The big idea here is to use the Pythagorean trigonometric identity, which is just cos alpha squared plus sine alpha squared is equal to 1, and get the value of sine alpha, which we'll then put into our area. That is a bit time-taking here, so I'll give it to you guys as homework. You should end up with something that looks like this. This is the area of a cyclic quadrilateral, where S is called the semi-perimeter. It's just the perimeter divided by 2. Now we're going to maximize this. But don't worry, we will not be taking the derivative of anything anymore. We are going to do this slightly more elegant with the AM-GM inequality. It states that the arithmetic mean is always bigger or equal to the geometric mean. As you can see, the area is looking very similar to our geometric mean. Maximizing the geometric mean means that it is equal to the AM. That only happens when this holds. From that, we can conclude that all the sides should be equal. If we were to see how that looks, that is obviously a square. Do you realize something? If I were to cut this circle in half, the rectangle on top has an area of r squared, and that is just our rectangle from the question at the start. Thank you everybody for watching this video. I hope you've learned something and had fun.